Assalamualaikum warahmatullahi wabarakatuh. Today we are going to discuss about our topic, which is simple harmonic motion. Before discussing our topic, I'm going to introduce our group members. First, Nazira Waida binti Muhammad, which is me, and then Aina Inshira binti Zubail, Nur Ain Batrisha binti Muhammad Adam Joanis, Nur Maisara binti Nur Azman, and lastly, Baitinuza binti Mahad Ghani. First, introduction. Time measurement has evolved over time, primarily based on periodic motion and duration. In the past, synchronization methods like water flow, incense, or wax burning were used. Our calendar system is closely related to celestial movement, with days defined by Earth's rotation, months by the month's orbit, and years correlated with the Earth's orbit around the Sun. The invention of clocks using gear-trained cyclic motion improved the division of hours. The modern era saw the definition of a second determined with unprecedented accuracy using radiation vibration from cesium-133 atoms. The transition to atomic timekeeping established the benchmark for time measurement, leading to the development of Coordinated Universal Time, they are also known as UTC. Second, problem statement. Objects with slow or subtle motions require acceleration, a feature difficult to evaluate from visual observation. Human perception is limited. Detecting even the smallest variation in velocity is difficult. External variables like distance, illumination, and human judgment can affect our motion perception. Using visual judgment alone can result in large errors in measuring an object's acceleration. So in this video, we will discuss the mathematical programming to measure the acceleration during simple harmonic motion.
Next, I will explain about the example for the problem of simple harmonic motion. A particle moves at a frequency of 0.5 Hz and an amplitude of 2 meters using simple harmonic motion. The particle's movement must be determined during a single oscillation at a given time, t equals to 3 seconds, in order to solve the issue. Plotting the particle's location as a function of time during the whole oscillation using RStudio is another step toward the answer.
Next, I am going to explain the mathematical programming part. First line, load the required library. We start by loading the ggplot2 library. This library is essential for creating sophisticated and customizable plots and visualization in R. Second line, constant for simple harmonic motion. Here, we define two constants for simple harmonic motion. First, amplitude represents the maximum displacement from the equilibrium position, and second, the frequency is the rate at which the motion repeats per unit of time. Next line, time array for one complete oscillation. We create an array of time values using the sec function. This array spans one complete oscillation based on the specific frequency, and it consists of 1000 equally spaced points. Next, position as a function of time. Using the sine function, we calculate the position of an object undergoing simple harmonic motion at each time point. The amplitude and frequency influence the range and speed of oscillation respectively. Next, calculate displacement at t equal to 3 seconds. Here, we calculate the displacement of the object at a specific time, t value, which is set to 3 seconds in this case. This provides the position of the object at that particular moment in time. Next, print the displacement at t equal to 3 seconds. We print the calculated displacement at t equal to 3 seconds using the cat function. This line serves as a simple output to inform the user about the position of the object at the specific time. Then, create a data frame for plotting. To facilitate plotting, we organize the time and position data into a data frame, DF. This step structures the data in a way that is suitable for to use with the ggplot2 package. Last, plotting the simple harmonic motion. Finally, we use ggplot2 to generate a line plot of the simple harmonic motion. The geom line function creates a line connecting the data points, and geom point adds to a red point at a specific time. The value to highlight it. Labels and a minimal theme are applied to enhance the clarity and aesthetics of the plot.
So now let's discuss about the graph that from the result the coding that we do before. So the graph depicts the position of a particle over the time in sine wave. So the graph that result from the provided are code for simulating and plotting simple harmonic motion. Okay, for the amplitude is set to 2.0, indicate the maximum displacement of the object from its equilibrium position. And for the frequency is set to 0.5, determine the number of oscillation that occur in 1 unit of the time. Okay, the result sine wave in the graph represent the oscillation motion of the object. The amplitude determine the height of the peaks and trough, while the frequency influence the number of oscillation within the given time range. Okay, for the graph title is set as simple harmonic motion, which is at x-axis is labeled as time, while the y-axis is labeled as position, which is m. Okay, for the overall appearance of the graph, minimalistic. Okay, for the interpretation, the sine wave demonstrate the periodic nature of the motion. The object oscillate between positive and negative position with a regular pattern. So, we can change the amplitude and frequency value to observe their effect on the shape of the graph. Higher amplitude will result in large oscillation, and higher frequency will lead to more oscillation within the same time interval. So, the graph provides a visual representation of simple harmonic motion, capture from the periodic oscillation of an object over the time.
As conclusion, the study of SHM involves a systematic process of identifying key constants such as amplitude and frequency, which serve as the foundation for understanding oscillatory behavior. The generation of a time array captures the dynamic of one complete oscillation at the chosen frequency. A red point on the plot indicates a prominent location within the oscillation, emphasizing the correlation between time and particle position. This detailed approach highlights the mathematical complexities of SHM and provides a tangible picture of the particle's motion. That's all from our group. Thank you for your attention.